Welcome back to QHSE Talks. Let me start with a simple question, one that most people in safety have never really stopped to think about. How much temperature change can the human body actually tolerate before everything starts to fail? We talk all the time about hazards you can see, moving equipment, chemicals, confined spaces, but today we're talking about something far more deceptive, something that doesn't look dangerous at first glance, something workers experience every single day and often underestimate until it's too late. Heat, cold, and the physiological limits of the human body. Because thermal stress isn't just uncomfortable. It's not just about sweating too much or feeling cold on the job. It's about pushing the human body outside the conditions it was designed to survive in and expecting it to keep performing anyway. And here's the part that should concern every safety professional, supervisor, and engineer listening right now. OSHA doesn't even give us a specific heat or cold stress standard to lean on. That means responsibility doesn't disappear. It intensifies. Under the General Duty Clause, employers are required to protect workers from recognized hazards, and thermal stress is absolutely a recognized hazard. The science is clear, the injuries are documented, the fatalities are real. What makes thermal stress especially dangerous is that it doesn't fail loudly. It fails quietly, progressively, physiologically. Your body compensates until it suddenly can't. And whether we're talking about heat stroke on a summer job site or hypothermia in cold, wet conditions, the underlying issue is the same. The human body operates within an incredibly narrow thermal window. Once you drift outside that window, even slightly, performance drops, judgment degrades, reaction time slows, and then, very quickly, survival itself comes into question. And that brings us to a concept that doesn't get nearly enough attention in safety discussions: the fragility of human thermoregulation. Because when we talk about heat stress and cold stress, we're not talking about comfort. We're talking about the margin between life and death.
And that word fragility, that's probably the most important piece of context we can set right now.
I agree.
Because when we talk about all this, the fundamental goal is so simple. But the stakes they're just massive.
Yeah.
It's all about keeping the human body in its very, very narrow survival range.
And that range is, it's remarkably tight. It should really make you stop and think.
What are we talking about exactly?
The source tells us the survival range for the human body is just between 97 degrees Fahrenheit and 100 degrees Fahrenheit.
That's it. Just 3 degrees.
Just 3 degrees. Our normal, our ideal core temperature is 98.6. The moment you start pushing that boundary below 97 or above 100, that's when all this critical, life-threatening science really comes into sharp focus.
Okay, so let's unpack that first half of the equation then. Let's talk heat stress.
Right.
The moment a worker steps into a hot environment, or even just starts intense physical work, their body immediately starts gaining heat. The guide details 4 fundamental ways this happens.
4 mechanisms, yeah. And understanding these is key because they dictate just how severe that heat stress is going to become.
So what's the first one?
The first mechanism is radiation.
Okay.
This is thermal radiation transfer between 2 or more objects that are not. They're not in physical contact.
So like electromagnetic waves.
Exactly. Think of it like this. The most obvious example is just standing outside on a sunny day. You feel that direct infrared heat from the sun hitting your skin.
Right.
But in an industrial setting, it's also standing near a massive hot piece of equipment, like the side of a boiler or a furnace. That radiant heat load is just nonstop, constantly transferring heat towards you.
Okay, so that's radiation. What's number 2?
Number 2 is convection. And this is the transfer of thermal energy through the movement of a heated fluid.
And by fluid, we mean liquid or, more commonly, air.
Usually air, yeah.
Yeah.
So imagine you're near a blast furnace.
Yeah.
If the air is hot but it's totally still, the convection might be minimal. You get this little layer of warmer air that builds up around your skin.
A sort of thermal barrier.
Kind of. But if a big fan kicks on and starts blowing that hot air directly on you,
Oh, that's a whole different story.
it's a whole different story. That convection transfer increases exponentially, and it just dumps heat onto your body. It's also, by the way, how a cold wind strips heat away so quickly. It's just cold convection.
Makes sense. Okay, next up is conduction. This one seems pretty straightforward.
It's the most straightforward. It's purely about physical contact.
Touching something hot.
Yep. The transfer of thermal energy between two objects that are physically touching. You lean your hand on a scorching hot pipe. You sit on a metal bench that's been baking in the sun. That heat is conducted directly into your body.
And you see that with tools, right? Tools left out in the sun or near a heat source.
Absolutely. It's a huge factor in settings where workers are handling equipment that has become, an extreme temperature.
So we have radiation, convection, and conduction. Those are all the external pressures.
Yeah.
But the fourth one, this is where it gets really interesting because the guide says this is the source of greatest concern.
Yes. The fourth source is metabolic heat.
So heat from the inside.
Heat generated from within the body, purely from the act of doing work. Every single muscle contraction, every movement, every bit of physical effort. It's all converting chemical energy into mechanical work.
And the byproduct is heat. A lot of heat.
A massive byproduct. And the source specifically highlights this as the source of greatest concern because it can rapidly overheat the body from the inside out, especially during heavy work. It can push your core temperature towards that 100-degree limit way faster than any external factor.
And that's a key distinction, isn't it? Because we can engineer controls for the other three.
We can.
We can put up shields for radiation. We can use ventilation for convection, insulation for conduction.
Well, you absolutely cannot stop the body from generating heat when it works. And the heavier the work, the faster that internal furnace burns.
We call that the internal load.
That's the internal load. So once the body starts accumulating all this heat, whether it's internal or external, it has to do something. It has to fight back.
And that's thermoregulation.
That's the body's natural immediate defense mechanism, thermoregulation.
And what does that actually look like
Right.
biologically? It's not a passive thing, right? It costs the body energy.
It costs a significant amount of energy and effort. Thermoregulation is the body's attempt to achieve what's called homeostasis.
That stable 98.6 core temperature.
Exactly, by expelling the excess heat. And the whole process begins with your cardiovascular system. Your heart starts to pump much more blood, it's forced to work harder, and that dramatically increases your cardiac output.
I can see the risk there immediately. If your heart has to work that much harder, that's a huge strain, especially for older workers or anyone with a pre-existing condition.
Precisely. That's a risk even before you get to actual heat illness. So at the same time, the body aggressively shunts this hot blood away from the core out towards your skin.
Okay.
The blood vessels expand, that's a process called vasodilation, to handle that increased blood flow. And the capillaries, which are right near the surface of the skin, they just fill up with this hot blood.
So the body is basically turning itself into a human radiator. It's trying to get the hottest substance, the blood, as close to the outside air as possible.
That is the goal. By circulating the blood close to the skin, that excess heat can be lost to the cooler environment through convection, conduction, and radiation.
And then that cooler blood goes back to the core.
It returns to the core, picks up more heat, and the whole cycle repeats over and over until either the core temperature stabilizes or the system gets overwhelmed.
And the most visible part of this whole process, the one we all know, is sweat.
Yes. Sweat and its partner, evaporation. The release of sweat is designed to maximize cooling. As that liquid sweat turns into a gas on your skin, it pulls a massive amount of heat away from the body.
It's called the latent heat of vaporization.
That's the principle. But here is the critical limitation. Evaporation depends entirely on the humidity and the airflow.
Right.
If the humidity is too high, the sweat can't evaporate. It just drips off you. And when that happens, the body's primary, most powerful cooling system just fails.
And the core temperature starts climbing fast.
It climbs rapidly toward that 100-degree danger zone.
Which is why just looking at a thermometer is such a bad way to judge risk.
Yeah.
You could be fine in 100-degree dry heat in Arizona, but 90 degrees with 90% humidity in Florida, that can kill you.
It absolutely can, purely because that evaporation is inhibited.
So moving from the physics of it to the consequences, let's talk about the actual illnesses, starting with something very common, heat cramps.
Okay.
The guide says this often comes from a misunderstanding of proper hydration.
That's right. It's a very specific chemical issue. Heat cramps. They show up as these painful muscle spasms. They can be really incapacitating.
And what's the cause?
The source is very clear. They happen to people who sweat a lot, losing tons of water and salt, but then they only drink large amounts of plain water. They fail to replace the lost body salts, the electrolytes.
So it's not just about dehydration, it's actually about diluting the electrolytes you have left.
Exactly. You sweat, you lose salt, you chug plain water, and that water rushes into your bloodstream, and it significantly dilutes the concentration of the electrolytes that are still in your system.
And that throws everything out of whack.
It completely upsets the delicate balance your muscle cells and nerve endings need to fire correctly. Your muscles need that salt, sodium, potassium to contract and relax. When the balance is wrong, the result is just painful, uncontrollable cramping.
So the prevention and the treatment are one and the same then. It's about fixing that chemical imbalance.
Very straightforward. Workers should drink plenty of fluids, yes, but they have to replace the salt. The guide notes that just normal salting of your food is usually enough for most situations.
But what about really extreme heat?
For high heat or heavy work, here's the crucial, actionable advice. In those extreme settings, it's strongly recommended that every third time a person takes a drink, it should be a sports drink or some kind of electrolyte solution.
So you're actively putting the salts back in.
This staggered approach helps maintain that essential balance your cells need to function.
Now, heat cramps are painful, but they're a warning sign compared to the real danger here. Heat stroke.
The source defines heat stroke plainly, unequivocally. It is a medical emergency.
This is the point of no return.
This is when the body's core temp has gone past 104 degrees Fahrenheit, and the whole thermoregulation system, including the ability to sweat, has often just completely failed.
Wow.
Immediate aggressive intervention is required to save the person's life and to prevent permanent brain damage. This is when that 100-degree line has been completely shattered.
Okay, so given how close that catastrophic failure is, let's walk through the prevention measures. The layered controls that safety professionals have to put in place. First up is acclimation.
Acclimation is absolutely foundational. It just means that workers have to be physically and physiologically conditioned to the heat.
You can't just throw someone into a hot environment.
No, you can't take someone who's been working in an air-conditioned office all winter and then suddenly put them on a road crew in July doing heavy labor. It doesn't work.
Sure.
Acclimation has to be gradual. Usually takes about 4 to 14 days, where you slowly ramp up the exposure and the workload.
And what's actually happening in the body during that time.
The body just gets way more efficient. The physiological responses improve. You start sweating sooner, your sweat becomes more dilute, which means you hold on to more salt, your heart rate stabilizes with less strain.
You're just better at dealing with the heat.
You're conditioning the body to use less energy to maintain that 3-degree survival window.
Okay, beyond getting the body ready, there are administrative controls, like timing the work.
Oh, absolutely. Scheduling is a key control. The heaviest work, the most metabolically intense work, the kind that generates the most internal heat.
Right.
That should always be done during the coolest part of the day.
Early morning, usually.
Early morning, before the sun is at its peak, before surfaces have heated up, and before ambient temperatures spike. Pushing that heavy labor into the midday sun just drastically increases the risk.
Another big one is a behavioral control, the buddy system.
The buddy system is critical. It means workers operate in pairs, and their job is to explicitly watch each other for the subtle signs of heat-related distress.
Why that's so necessary?
Because the symptoms, things like confusion, dizziness, irrational behavior, loss of judgment, these are key signs of heat stress. A person who is suffering from heat exhaustion or impending heat stroke might genuinely not recognize their own danger.
Because their buddy is your safety net.
Your buddy provides that crucial external check and is responsible for getting help.
Let's get specific on hydration, because the guide gives us a very clear rule of thumb here.
Yes, fluid replacement has to be precise. It has to be continuous, not just when you feel thirsty.
Because by then it's too late.
It's too late. The specific recommendation is that workers should aim for 1 cup, about 8 ounces of water, or an electrolyte solution every 15 to 20 minutes.
Every 15 to 20 minutes.
During periods of exertion in the heat, this steady, measured intake is vital. It keeps the body ahead of the fluid loss curve.
Okay, and what about clothing?
Clothing should always be light, loose-fitting, and breathable.
That seems obvious, but people get it wrong.
all the time.
Mhm.
This allows for maximum cooling across the skin and gives your sweat the best chance to evaporate. You have to avoid tight, dark clothing that just absorbs and traps radiant heat.
And there are also things to avoid consuming.
Yes, avoid caffeine and alcoholic beverages. They're diuretics. They actively make you lose fluid, which interferes with your body's ability to stay hydrated and stable. It just accelerates dehydration.
Finally, we have to talk about PPE, personal protective equipment.
This is a tough one. Because even though required PPE like respirators or chemical suits or heavy gloves can sometimes significantly increase the thermal burden,
By trapping heat.
by trapping heat and stopping evaporative cooling, it still has to be worn if the job requires it.
So what's the solution?
The safety professional's role becomes essential. They have to adjust the workerist cycles, which we're about to get into, to strictly compensate for that extra heat load caused by the PPE.
Yeah.
All these measures, they're the layered defense against breaking that 3-degree survival window.
All right, this is where we really get into the deep dive. We're moving from strategies to the hard science, the mathematics that professional safety is built on.
Right.
The ultimate goal of measuring all these thermal factors is to quantify the risk. Why do safety professionals use these complicated formulas instead of just, looking at the thermostat on the wall?
Because you can't manage a risk effectively if you can't measure it. The goal of these measurements, specifically the average metabolic rate, or MFG, and the wet bulb globe temperature, the WBGT index,
MFG and WBGT.
is to establish safe, scientifically justifiable work rest cycles. And these are based on the ACGIH threshold limit values, the TLVs we mentioned earlier.
And remind us, what is the ACGIH?
The American Conference of Governmental Industrial Hygienists. They're a non-governmental body, but they set the widely accepted science-based standards for workplace exposure. Their TLVs are the gold standard.
So these are the conditions under which basically all healthy workers can be exposed without getting sick.
That's the idea. And they are the anchor for this whole conversation.
So to use their tables, we need to quantify two things: the internal heat load and the external heat load.
Exactly.
Let's start with part A, calculating the average metabolic rate, MEG. This is how much heat the employee is generating internally.
Correct. We use a time-weighted average equation to figure out the overall rate of internal heat generation during a shift. It's designed to account for all the different things a worker does, from heavy lifting to sitting on a break, and weigh them based on how long they do each task.
And the formula is?
The formula is MAVG equals M1 times T1 plus M2 times T2 and so on, all divided by the sum of T1 plus T2 and so on.
So it's a standard weighted average. M is the metabolic rate in kilocalories per minute, and T is the time spent on that activity in minutes.
That's it. And the individual M values, you don't guess them, you get them from standardized tables in the guide. These tables have meticulously assessed different kinds of work based on body position, muscle use, all of it.
So sitting still might be, 0.3 nacal per minute?
And operating a heavy jackhammer might be 7.0. We use these standard inputs to quantify the physiological cost of the work.
Okay, to make this real for everyone listening, let's walk through the detailed example that's in the source material. It assesses a worker's varied 8-hour shift.
All right. We've got 4 distinct activities across 8 hours, so that's 480 minutes total. Each one has its own metabolic rate and duration.
Let's break it down. Activity 1 is shoveling gravel. That's heavy work.
Heavy work.
The metabolic rate, M1, is 7.0 kcal per minute. The duration, T1, is 1.5 hours. So we have to convert that to minutes.
Always convert to minutes. So 1.5 times 60 is 90 minutes.
So the first part of our calculation is 7 times 90.
M1 times T1, exactly.
Okay, activity 2, taking a scheduled break. This is sitting down.
So that's light work or rest. The metabolic rate, M2, is just 0.3 kcal per minute, and the duration, T2, is 30 minutes.
The second term is 0.3 times 30.
And this is critical. It acknowledges that even when you're resting, your body is still generating a baseline amount of internal heat.
Right. Activity 3, constructing a concrete form. This is moderate work.
Moderate work, yep.
The metabolic rate, M3, is 3.5 kcal per minute. And the duration, T3, is 4 hours, which is 240 minutes.
So that's M3 times T3. 3.5 times 240. And that's the longest activity, so it's going to carry a lot of weight in the final average.
And finally, activity 4, pouring and finishing concrete. This is pretty demanding, almost heavy.
It is. The metabolic rate for that, M4, is 5.0 kcal per minute, and the duration, T4, is 2 hours or 120 minutes.
So the last term is M4 times T4, 5 times 120.
Correct. Now we can put it all together.
Okay, let's calculate the numerator first. That's the total accumulated internal heat.
Mhm.
So M1T1 was 7 times 90, which is 630.
630 kilocalories.
M2T2 was 0.3 times 30, so that's 9.
Just 9 kcal for the break.
M3T3 was 3.5 times 240, which comes out to 840.
840.
And M4T4 was 5 times 120, which is 600.
Right.
So we add those all up. 630 plus 9 plus 840 plus 600, that gives us 2,079 kilocalories.
2,079. That's the total physiological cost in heat energy that the worker paid over that 8-hour shift.
And the denominator is just the total time, right?
The total time, which we know is 480 minutes.
So the final calculation for the average metabolic rate, MAAG, is 2,079 divided by 480.
And that gives us
An average metabolic rate of approximately 4.33 kilocalorie per minute.
4.33.
So now we have it. We've quantified the internal pressure on this worker's body. What does that number, 4.33, immediately tell a safety professional?
That number is critical. It tells them that the work profile itself, just the work, forget the weather for a second, falls squarely into the moderate to heavy work category.
Okay.
The ACGIH tables classify anything from 3.0 to 5.0 kcal per minute as moderate to heavy. This means that worker is consistently expending energy equivalent to, say, a very brisk walk or heavy construction labor.
So that high internal heat generation immediately raises a red flag.
It immediately triggers the need for measured work rest cycles and continuous monitoring, even if the environment doesn't feel terribly hot.
That makes perfect sense. So we know the worker is generating an average of 4.33 kcal per minute of heat internally. Now we have to measure the external pressure.
Yeah.
And that's part B, calculating the wet bulb globe temperature index, or WBGT.
The WBGT index. This is the global standard for thermal safety because it accounts for 3 crucial factors that a simple thermometer just completely ignores: air temperature, humidity, and radiant heat. It's a compound measurement that really reflects the environmental stress on the body's ability to cool itself.
So what are the 3 key temperature inputs that we combine to create this index?
They're all measured with specialized instruments. First, and most important, is WB, the wet bulb temperature.
Okay.
This is measured by a thermometer with its bulb covered in a wet cotton wick. The temperature is lower because of evaporative cooling. If the air is very dry, the water evaporates fast, and the temperature drops a lot. If the air is very humid,
Evaporation slows down, and the temperature stays high.
Exactly. So the WB reading is a direct reflection of how effective your sweat is going to be at cooling you down.
Okay, what's next?
Next is DB, the dry bulb temperature. This is just the standard air temperature we're all used to. It's actually the least impactful variable in the whole risk assessment.
And the third one?
The third is GT, the globe temperature. This is measured by a thermometer inside a big, hollow, matte black copper globe. Because the black surface absorbs radiant heat from all sources: the sun, hot walls, machinery, hot pavement. So this reading measures the total radiant heat load from the surroundings.
So we have these 3 readings, WB, DB, and GT. And the guide gives us 2 different formulas, depending on the conditions.
That's right, because the environment dictates which factors are most relevant.
Let's start with the one for when the sun isn't a direct factor.
For indoor and outdoor conditions with no solar load, so a heavily overcast day, or working inside a warehouse, the dry bulb temperature is essentially ignored. The formula focuses on the 2 biggest challenges: humidity and radiant heat.
And that formula is?
WBGT equals 0.7 times the wet bulb temperature plus 0.3 times the globe temperature.
That weighting is really telling. 70% of the entire measurement comes from the wet bulb.
70%?
Meaning humidity, or the lack of effective cooling, completely dominates the risk calculation.
That 70% weighting is no accident. It is the scientific acknowledgement that high humidity is the single most restrictive environmental factor stopping the body from staying in that 3-degree survival window.
But if the sun is out, if there's a big solar load, the formula changes.
It expands slightly. For outdoors with a solar load, the formula becomes WBGT equals 0.7 times the wet bulb plus 0.2 times the globe temp plus 0.1 times the dry bulb.
So even with direct sun, the wet bulb is still 70% of the equation.
It is always the heavily dominant factor. It just confirms that your body's inability to sweat efficiently is the greatest environmental determinant of heat stress risk in almost every situation.
And for a safety officer, that 70% weighting means you have to be aggressive with worker cycles, even if the air temperature feels only mildly hot.
The physics dictates the protocol. So now the safety professional has both pieces. They've calculated the MFG, the internal heat load, in our example, 4.33. And they've measured and calculated the WBGT index, the external heat load. They combine these two objective quantified metrics.
And this is where they go to the TLV tables.
This is where they go to the standardized ACGIH tables. They cross-reference the internal workload, or moderate to heavy work, against the specific external thermal environment, the WBGT.
And the table tells them what to do.
The table will prescribe the required work risk cycle. For instance, if the MMG is 4.33 and the WBGT is high, the table might say you need a 25% work, 75% rest cycle, or it might even require stopping work entirely.
So this is how thermal safety moves from just being based on how people feel to being based on precise quantitative risk management.
That's the goal.
Okay, we have spent a lot of time on heat gain and heat dissipation, the battle to keep the core temperature from rising above 100 degrees.
We have.
Now we need to talk about the counterpoint, cold stress, the battle to keep the core temperature from dropping below 97 degrees.
It's the exact opposite challenge, yes. Cold stress is what happens when your body's internal heat is lost to the colder environment faster than you can generate it.
So all your body's systems have to divert energy just to survive, not to do work.
Precisely. And this brings us right back to the physics of heat transfer, but we're looking at it in reverse.
The body is losing heat through those same four mechanisms.
The same four: radiation, conduction, convection, and evaporation.
Okay, so with radiation, my body is just radiating heat out into the cold air.
Exactly. You are the heat source. And conduction is especially dangerous in the cold. We talked about touching a hot pipe.
Yeah.
Now think about grabbing a frozen metal tool without gloves.
Oh, yeah.
Or leaning against a cold concrete wall. Your body heat just flows rapidly into that frigid material. It's a massive safety hazard.
And convection is magnified, too. That's the wind chill factor.
It's the great heat thief. Cold air moving past your skin just strips away that warm little layer of air your body tries to create. A slight breeze in 40-degree weather can feel dramatically colder because convection is just aggressively pulling heat away from you.
And what about evaporation? This one seems counterintuitive in the cold.
It is, but it's so important. Evaporation is still a huge heat loss mechanism, especially from wet clothing or sweat if you're working hard.
So a worker doing heavy labor in the cold,
Yeah.
they might actually be putting themselves at greater risk.
That's often the biggest mistake people make in cold weather work. You generate enough metabolic heat to sweat heavily, you saturate your inner clothing layers, and the moment you stop working, that moisture rapidly accelerates heat loss.
Because wet clothing is a terrible insulator.
Terrible. It dramatically increases the speed at which you can drop below that 97-degree threshold.
So beyond the direct threat of, freezing, the source points out that cold stress creates these critical indirect safety problems.
Yes. When you're physically uncomfortable from the cold, your brain's priority shifts. It moves from the task at hand to just managing your discomfort.
And that leads to inattention.
A massive reduction in situational awareness and focus. Inattention. That's when accidents happen, when errors are made, when tools are dropped.
And that combines with rapid fatigue.
Because cold stress makes you get tired much faster. Your body is expending immense amounts of energy just shivering, just trying to keep your core warm. That burns through your energy reserve so much faster than normal, leading to quicker exhaustion and, again, a higher probability of injury.
So let's talk about the prevention strategies for cold. What are the key controls?
Well, engineering controls focus on reducing the exposure. Things like using heated shelters or heated cabs for machinery operators. And administratively, it's about mandating frequent scheduled rest breaks in a warm, heated environment.
So just like heat safety has work cycles, cold safety needs mandated warm-up cycles.
Exactly. And then a huge part of it is clothing.
The layering principle.
The 3-layer principle? Yes. First, a wicking layer right next to your skin, something like polypropylene to pull moisture away. Second, an insulation layer like fleece or wool to trap air. And third, an outer shell that's windproof and water-resistant to protect against that convective heat loss from the wind.
And loose layers are better than one big, bulky coat.
Far more effective.
Okay, now let's categorize the actual injuries. The guide splits them into two types based on the temperature.
That's right. First, we have non-freezing injuries. These happen when the environmental temps are actually above 32 degrees Fahrenheit, but the exposure is prolonged or it's damp.
What are some examples of those?
Things like chilblains, which are these inflammatory lesions from repeated exposure to near freezing but not actually freezing temperatures, or immersion injuries like trench foot from prolonged exposure to cold, damp conditions.
And this category also includes hypothermia.
Crucially, yes, mild, moderate, and severe hypothermia. This is the systemic danger of your core temperature dropping below 97 degrees.
What's the difference between the levels?
Well, mild hypothermia, down to about 90 degrees, involves violent shivering, difficulty with complex tasks. Moderate hypothermia, down to about 82 degrees, is where the shivering actually stops. You get muscle rigidity, slurred speech. This is where judgment is gone.
And severe.
Below 82 degrees, that can lead to loss of consciousness and cardiac arrest. It is a direct assault on the core temperature your body needs to survive.
And the other more severe category is freezing injuries.
These happen when temperatures fall below freezing, below 32 degrees Fahrenheit. The main example here is frostbite of varying degrees.
And this is when tissue actually freezes.
This is the actual freezing of tissue.
Yeah.
Water crystals form inside your cells, causing direct cellular damage, especially in your fingers, toes, and nose.
And it's important to know the difference because the first aid is completely different.
Right? Completely. Gently rewarming someone with mild hypothermia is vastly different from treating tissue that has actually frozen solid, which requires specialized, rapid rewarming to try and save the limb. The protocol has to be tailored to the specific condition.
So we've covered a tremendous amount of ground today, from the microscopic biology all the way to the macro-level math and safety management.
We have.
Before we wrap up, let's just revisit the most critical nuggets for you, the learner, to take away from this deep dive.
Okay, first is understanding the thermal dynamics. You have to remember the 4 sources of heat gain or loss: radiation, convection, conduction, and metabolism. They're always operating.
Second, always appreciate the unique role of metabolic heat in occupational settings. That internal heat from work. It's the source of greatest concern because it can drive your core temperature up so fast, no matter what the thermometer says.
Third, never ever diminish the severity of the illnesses. Heat stroke is a medical emergency, full stop. It requires immediate aggressive action. That's why prevention, like acclimation and the buddy system, is non-negotiable.
And finally, the cornerstone of professional thermal safety. The dual metric approach.
The dual metric approach. You must combine the internal heat load, that MAVG calculation, with the external environmental load, the WBGT index.
It's the only way.
It's the only way. By pairing MAV and WBGT, and by understanding that 70% of that environmental risk is usually dictated by humidity, safety professionals can use those standard ACGIH tables to set precise, defensible, and life-saving work risk cycles.
That brings us to our final provocative thought. Our entire discussion today has been about the incredible effort required to maintain human homeostasis. We keep coming back to that tiny 3-degree survival range, 97 to 100 degrees Fahrenheit.
A profoundly narrow, incredibly fragile band of stability. So, given the massive engineering, administrative, and physiological effort it takes just to maintain that window in a controlled environment like a construction site, consider the broader implications. What does the extreme fragility and narrowness of this window tell us about the vulnerability of the human system when it's faced with sustained environmental instability? Think about global climate change. The difference between life and death is managed by single degrees.
Food for thought indeed, as you evaluate the environments around you, whether it's at work or just in the world at large. Thank you for joining us for the deep dive.
We'll see you next time.